So we're now going to begin lecture notes week 11. And if you take a look at the introduction, if you remember from the trigonometric equations that we were graphing, we used the fact that if sine was if sine was odd, then having a negative inside of the argument meant that we could bring the negative outside and multiply it with the function. Whereas if you had an even function like cosine, then f of negative x is the same as f of x. So these equations are actually called identities. They are examples of identities because that is something that is true regardless of what value you replace for x. So it's true for every x, and when that is the case, you have an identity. And so those are just two of several other identities that exist for trigonometry. If you take a look at Canvas under the module for this week, you'll find a sheet that is called Formulas and Identities. And this contains several other equations that are true for any variable that you decide to plug in. So again, when you have that situation, then you have an identity. So we're going to be considering these to solve all of the problems in the lecture notes for the next couple of weeks. Okay. So let's start by looking at this first type of problem, which is finding the exact trig values of angles that are not on the unit circle. So on the unit circle, we found angles that are multiples of 45 or multiples of 30. And it allowed us to quickly pick out what is the sine, what is the cosine, and what is the tangent. For other angles that are not on the unit circle, such as maybe 15 degrees, we can still solve that without using a calculator by applying maybe sum or difference, double angle, or half angle formulas. So I'm going to start by looking at the sum and difference formulas. So sum and difference are found on the left-hand column at the top, on the right-hand column at the top. And we're just going to kind of dissect these a little bit. It looks a little bit scary because it has this plus or minus, but it's actually not as bad as it looks. This just contains two formulas in one. And on a sticky, for instance, I'm going to focus on this first one. I'm going to separate it into the two equations that are being contained here. So we have sine of A plus B, and I'm going to be using capital A and capital B instead of alpha and beta so it doesn't look as scary. If we just focus on the top symbol, which is a plus, okay, so if we focus on the top symbol on the left-hand side, then we also have to pick out the top symbol on the right-hand side. And so that is saying that the sine of A plus B is the same thing as taking sine of A, taking cosine of B, multiplying it together, and then adding it to the product of cosine of A times sine of B. And that's the first equation that's contained in there. The second equation is if you take the bottom symbol, so on the left-hand side we have a negative, on the right-hand side we also have a negative. So the second equation, or the second identity, would be sine of A minus B is equal to sine of A cosine of B minus cosine of A sine of B. It's just the symbols change. For cosine, it's a similar idea. If I take just the top symbol, we would have cosine of A plus B is equal to cosine of A cosine of B minus sine of A sine of B. And the reason being, again, is because if I take the top symbol on the left-hand side, then I also have to take the top symbol on the right-hand side. Okay, so if on top we have plus, then over here at the top we have minus, and this is the equation that we get. If we now consider the bottom symbol, then that means that we'll have an equation that reads, or an identity that reads cosine of A minus B is equal to cosine of A cosine of B plus sine of A sine of B. Alright, so let's use the sum and difference formulas to help us solve part A, which is asking us to find cosine of 15 degrees. Now to solve this type of problem, what we do is we take the angle and we try to write it as either a sum or a difference of two angles that are on the unit circle. And so if we think about 15 degrees, we could take 45 degrees minus 30, and that'll give us 15. So I'm going to rewrite this as cosine of 15 degrees is equal to cosine of 45 degrees minus 30 degrees. Now the reason why we would want to do that is because now I can use one of my sum and difference formulas, specifically this last one that we dissected, because it falls in line with the form, right? We have the difference of two angles. The A in our case is 45 and the B is 30 degrees. And so therefore, according to this identity, what this should be equal to is cosine of the first angle, angle A, which is 45 degrees, times cosine of the second angle, which is 30 degrees, plus sine of the first, which is 45 degrees, times sine of the second, which is 30. And then hence the reason why we want to write it in terms of angles that are on the unit circle, because now we can simply refer to it and find out what is cosine 45, what is cosine 30, and same for the sine function. Okay. Alright, so here is my unit circle. I have it handy from a set of lecture notes that we've considered in the past, lecture notes week 3. And if I take a look at 30 degrees, cosine of 30 is radical 3 over 2. Actually, yeah, so this is going to be radical 3 over 2. If I take a look at cosine 45, that's going to be a radical 2 over 2. And then we have plus sine of 45 is also radical 2 over 2. And sine of 30 is going to be 1/2. Okay, so if we take this product here, we're going to end up with the square root of 2 times square root of 3, which is a square root of 6, over 2 times 2, which is 4, plus a square root of 2 over 4, because square root of 2 times 1 will give us still square root of 4. So altogether, the most we can do is combine the numerators into one fraction as square root of 6 plus square root of 2 all over 4. If we repeat the idea of with sine of 75 degrees, we're trying to write it as a sum of two angles that are on the unit circle. So we could potentially write this, or one way to do it, as sine of 45 degrees plus 30 degrees, right? Sine of 45 plus 30 gives us 75. So now if we look at the formula for sine, specifically the one that has plus, right, because that's the one that aligns with the form we have here, we get that A is going to be like the 45 degrees, and B is going to be like the 30 degrees. Okay, so now if we apply the formula, we're going to get sine of 45 degrees times cosine of 30 degrees, because it's sine of the first angle times cosine of the second. And then we have plus cosine of the first angle, so that'll be 45. times sine of the second. So times sine of 30 degrees. And so again, if we look at the unit circle, we'll find that the sine of 45 is radical 2 over 2. Cosine of 30 will be radical 3 over 2. Cosine of 45 is going to be radical 2 over 2. And sine of 30 will be 1/2. So in the end, we're going to have a square root of 2 times the square root of 3, which is a square root of 6, over a 2 times a 2, that's a 4. And then this is a square root of 2 times 1 over a 2 times 2, which is 4. So we end up getting the same answer, which maybe might seem a little suspicious to us. We can always double check on the calculator. So let's go ahead and do that. So if we look at the calculator, I'll make sure that I change to degree mode. Sine of 75 degrees is equal to 0.9659. And if I take a look at what is cosine of 15 degrees, we get exactly the same thing. So it must mean that these two fractions have to equal to this decimal answer. And we can double check. So let's take the square root of 6 plus the square root of 2 divided by 4. Make sure that you group the numerator together, otherwise you're just going to divide the radical 2 by 4. So grouping the numerator together gives us this decimal, which agrees with the cosine and sine. Okay, so that looks good. So for part C, we have cosine of 5 pi over 12, which means that we're switching now to radians, and there are two methods that you can take in order to approach this problem. The first one is you can change the radians to degrees by multiplying 180 over pi into this 5 pi over 12. And then from there, trying to find two angles that add up to the degree answer, or that subtract to the degree answer. The other option is to find what two angles in radians add up to 5 pi over 12, or have a difference of 5 pi over 12. I like to do it at sum to 5 pi over 12, because what I do, and this is more of a trial and error approach, what I do is I break up the 5 pi over 12 into the sum of maybe pi over 12 plus 4 pi over 12, right? And then I check if these two reduce to any answer, any angle that is on the unit circle. So if pi over 12 doesn't reduce, 4 pi over 12 reduces to a pi over 3. This is on the unit circle, but pi over 12 is not. So because there's at least one angle that is not on the unit circle, we kind of discard this possibility. The next possibility we can take a look at is now having the sum of 2 pi over 12 plus 3 pi over 12. Now if we write it this way, the 2 pi over 12 reduces down to a pi over 6, and the 3 pi over 12 reduces down to a pi over 4. Now both of these are on the unit circle, so because both angles are, we use that possibility. So coming back here, it means I'm going to write that cosine of 5 pi over 12 is the same as taking cosine of pi over 6 plus pi over 4. And now we'll go back to our formulas and identities. The formula that best fits the form we have here is this cosine of a plus b, where a is the pi over 6 and b is the pi over 4. Okay. So with that in mind, the identity reads that should be equal to cosine of the first angle, so that'll be cosine of pi over 6, times cosine of the second angle, so that'll be a pi over 4, minus sine of the first angle, so minus sine of pi over 6, times sine of the second angle. So that'll be times sine of pi over 4. Okay, again, let's go to the unit circle. Here is pi over 6. Cosine of pi over 6 will be a radical 3 over 2. Pi over 4 is here. Cosine of pi over 4 is a radical 2 over 2. Okay. Pi over 6 is here again, and sine of pi over 6 is 1/2. And finally, sine of pi over 4 is here, and sine of pi over 4 is radical 2 over 2. Okay, so what do we get? Radical 3 times radical 2 is a radical 6 over 2 times 2, that's 4, minus 1 times radical 2 is radical 2, over 2 times 2 is 4. So the final answer is square root of 6 minus square root of 2 all over a 4. We're going to attempt one more problem of that type. In this case, we have a 7 pi over 12. So we'll go through with that same trial and error approach. So we'll first start maybe with pi over 12 plus 6 pi over 12, because together they add up to 7 pi over 12. But the issue with that is that the first fraction, the pi over 12, is not going to reduce down to anything useful, nothing on the unit circle. Right, so this one doesn't work because the first fraction is not, the first fraction fails. The next one to try is maybe a 2 pi over 12 plus a 5 pi over 12. Now in this case, the 2 pi over 12 reduces down to a pi over 6, which is on the unit circle, but the 5 pi over 12 does not reduce, and that is not on the unit circle. So that means we don't use this option. And the next one we can try is a 3 pi over 12 plus a 4 pi over 12. And 3 pi over 12 will reduce down to a pi over 4. That is on the unit circle. And then the 4 pi reduces down to a 3 pi over, a pi over 4. All right, divide top and bottom by 4, and we'll get a pi over 3. So this is also on the unit circle. That means that we can write down 7 pi over 12 as a sum of pi over 4 plus pi over 3. And so we'll write it here. Tangent of 7 pi over 12 is the same as tangent of pi over 4 plus pi over 3. And now we didn't really dissect the formulas for tangent, so let's look at them directly on the formula sheet. Okay, the one that we're looking for is one that has plus. So here, that would be the top symbol. And so picking the top symbol on the left-hand side means picking the top symbol everywhere on the right-hand side. Okay, so let's write it here on our sticky note. We'll have tangent of a plus b is equal to, in the numerator, tangent of a plus tangent of b. So that's tangent of a plus tangent of b over 1 minus tangent of a tangent of b. Okay, and so now that we have the formula, we can come to this problem and start replacing in some values. So tangent of a, that's pi over 4 plus b, which is pi over 3, will be tangent of the first angle. That's tangent of pi over 4 plus tangent of the second angle, that's tangent of pi over 3, divided by 1 minus tangent of the first angle times tangent of the second angle. And all of that is in the denominator. So we can refer to our unit circle, and in the unit circle, what we have to keep in mind is that we have explicitly sine and cosine. Cosine is the x-coordinate, sine is the y-coordinate, but we can always find what tangent is by remembering that tangent is y over x, or in other words, sine over cosine. You can also find that same formula that I just mentioned on the formulas and identity sheet at the very top. Okay, tangent of angle theta is going to be sine of angle theta divided by cosine of angle theta. Okay, so here, what we're going to do is take the, look at pi over 4. So here's pi over 4. Take sine of pi over 4, which is going to be radical 2 over 2, and divided by cosine of pi over 4, which is also radical 2 over 2. So this is going to be just 1. We'll have a 1 plus. Now tangent pi over 3, here's pi over 3. We'll have y over x again, or sine over cosine. So that'll be a square root of 3 over 2 divided by a 1/2. That's the same thing as having a square root of 3 over 2 times a 2 over 1. So we're just going to get a radical 3. Okay, and then in the bottom we'll have 1 minus tangent of pi over 4, which we said was 1, times tangent of pi over 3, which we said is radical 3. Okay, so in the end, well, not completely the end, because we have 1 plus square root of 3 over 1 minus radical 3. And if you recall, we don't like to leave radicals in the denominator for any problem. So to rationalize 1 plus radical 3 over 1 minus radical 3, we go through the following steps. We actually multiply by the conjugate of the denominator. And the conjugate simply means we have the same two terms but the opposite sign in between them. So we're going to be multiplied by 1 plus radical 3 at top and bottom. And then if we distribute, 1 times 1 will give us this 1. Then 1 times radical 3 will be a radical 3. Radical 3 times 1 will also give us radical 3, so that's a total of 2 radical 3's. And then radical 3 times radical 3 will give us just 3. In the denominator, 1 times 1 will give us 1. 1 times a radical 3 will give us a positive radical 3. Then negative radical 3 times 1 will give us the negative radical 3. Negative radical 3 times radical 3 will give us a negative radical 3 squared, which is just 3, so minus 3. If we combine the like terms in the denominator, well, the plus radical 3 and negative radical 3 are going to cancel out, leaving us a 1 minus radical 3, so that's this here. And then in the numerator, if we take the 1 plus 3, it'll give us a 4 plus 2 radical 3. In the denominator, the 1 minus 3 will give us negative 2. If we then take those two terms and split them up, we'll get a 4 over negative 2 plus 2 radical 3 over negative 2. And then the 4 over negative 2 will reduce down to a negative 2, and the 2 over negative 2 will simply reduce down to a negative 1, radical 3. So negative 2 minus radical 3 would be our final answer for part D. We're now going to take a look at a different type of problem in which we have more than one term and we have a product of potentially two trigonometric trigonometric terms, or maybe even squares, as in the case of G and H. So for this one, we have cosine of 87 degrees times cosine of 93 minus sine 87 sine of 93. So if we look again at the sum and difference formulas that we were considering earlier, it looks like this form might match one of the right-hand side part of an identity. In particular, if you take a look at the cosine of a plus b, that's cosine of the first angle times cosine of the second minus sine of the first times sine of the second. And that's precisely what we have, where we have the product of two cosines of different angles minus the product of two sines of different angles. So this is actually going to be equal to cosine of the first angle, which is 87 degrees, plus the second angle, which is 93. And so 87 degrees plus 93 degrees is going to give us 180. And that means that we have a final answer of -1. And if this seems a little bit suspicious that we might have something as complicated looking as cosine 87 times cosine 93, minus all this other stuff be just 1, we can always verify on the calculator. On the calculator, let me just make sure we're in degree. Yep. If you take cosine of 87 degrees times cosine of 93 degrees minus sine of 87 degrees times sine of 93, we get -1, which is precisely the answer that we got from the law of cosines, the sum of cosines. Okay, similarly for part F, we have sine times cosine of two different angles minus cosine times sine of the same two angles. So if we consider which one best matches that form, we have sine of A times cosine B minus cosine A sine B, which fits perfectly with this. And that is equal to sine of the difference of the angle, sine of A minus B. So this is actually going to be sine of angle A, which is 40 degrees, minus angle B, which is 160. And so that's going to give us sine of -120. Now, if you recall, sine is an odd function, which means that when we have a negative inside of the argument, we can bring it out. So we get negative sine of 120. And now if we use the unit circle to help us find what is sine of 120, we're going to get a radical 3 over 2. So this is going to be radical 3 over 2, but we can't forget to bring over that negative. So we're going to have a negative. Okay. The next problem reads sine of 15 degrees times cosine of 15 degrees. Now that doesn't look like any of these equations because both, all of these equations have two terms, right? They have the product of two trig plus or minus the product of two other trig functions. So it's not really any of these formulas, which means that we have to refer back to our cheat sheet and see if there's anything that might fit better. Yeah. So take a moment to look through the formulas. And there is actually one here that looks very similar to what we have. We have sine times cosine, and if you look at the fourth product to sum formula, and not the fourth, the third product to sum formula, we have sine of an angle times cosine of an angle equals 1/2 times sine of the sum of the two plus sine of the difference of the two angles. And so I'm actually going to write that formula over here so that we can compare it. And we have sine of A times cosine of B is equal to 1/2 sine of A plus B plus sine of A minus B. Okay, so now if we compare the two, this left-hand side agrees. So if we replace A with 15 and B with 15, that means that we have sine of 15 degrees times cosine of 15 degrees is equal to 1/2 sine of the first angle, which is 15. And I'll just go ahead and color code these. So we'll have 1/2 sine of first angle 15, second angle is also 15, plus sine of first angle 15, second angle is also 15, and that's a minus. We get 1/2 sine of 30 degrees plus sine of 0 degrees. Sine of 0 will be 0. Sine of 30 degrees, if you refer to the unit circle, is 1/2. So we'll end up having 1/2 times 1/2 plus 0. And that's simply going to be a 1/2 times a 1/2, which is 1/4. Okay, next problem. This one is even more interesting because now we do have a difference of two terms, but there's a square involved. So product to sum is not going to be enough because product to sum is just product of two factors. And sum and difference is not going to be enough because we don't have a square anywhere. So the formulas that have a square are the half angle formulas. We also see Pythagorean identities having some squares in them. And we also have squares in the double angle formulas. The form that we have is cosine squared, cosine of one angle 15 minus sine squared of the same angle 15. And the one that best fits that form is this double angle formula for cosine. Okay. So cosine of 2 theta has 3 different applicable formulas. This is the first one, here's the second, and here's the third. But the one that we're going to focus on is the cosine squared minus sine squared. So let me write this down, the formula. We have cosine of 2 theta is equal to cosine squared theta minus sine squared theta. And I'll just write here, this is a double angle formula. I didn't write it for this one, but I'll write it now. This was a product to sum. Okay. And now, because these two match, I'm simply going to write this as cosine squared of 15 degrees minus sine squared of 15 degrees. That is going to equal to cosine of 2 times 15 degrees. Right, I'm replacing everywhere there's a theta with 15 because these agree. Okay, then that'll give me a cosine of 30 degrees. And cosine of 30 degrees, if you take a look at the unit circle, that is going to be a square root of 3 over 2. Our final answer for this problem is a square root of 3 over 2. Alright, so today we're going to begin our week 12 and 13 set of lecture notes. Hopefully, my plan is to make it up to page 6, but we'll see where we get to. This is going to be dealing with identities and formulas, trigonometric identities and formulas. That has been posted under the lecture notes, and if you print it out, it's 4 pages. The first page looks like this, but we're not going to be focusing on that page too much. Rather, the one that we want to look at is the formulas and identities, which would be page 2. So if you don't have this handy, I do encourage you to have it maybe out on your phone or on a tablet. And when you have a chance, print it because it's going to be something that we're going to be referring to over and over again for the rest of the lecture notes that we're going to be considering. So the first type of problem that we're going to be dealing with are finding function values given information on some angle theta. And so the ones that we want to consider for these types of problems are the fundamental, the cofunction, the sum and difference, double angle, and half angle formulas. And so to determine which one of those, what formulas we're referring to,
they're all labeled. So for instance, the fundamental is referring, well, okay, that's probably the only one that's not explicitly labeled, but the fundamental refers to these first two sets, tangent and cotangent identities and the reciprocal identities. These are known as the fundamental. And if you take a look at what they are, these we've learned before. We've learned before that tangent is sine over cosine, and that cotangent is cosine over sine. We've also learned that cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tan. And the same thing is true about sine, cosine, and cotangent. They are the reciprocal of cosecant, secant, and cotangent respectively. Okay, so these are known as the fundamental. The cofunction formulas are down here. We also have sum and difference, which are here, double angle, which are here, and half angle, which are here. Okay, so those are all the formulas that we're going to be considering, and we'll learn how to use them as we approach different problems on the set of lecture notes. So let's look at example number 1. Find one value of theta or x that satisfies the following. Okay, so in this case, we have cotangent is equal to tangent of 25 degrees. So they're asking us what angle theta has a cotangent value that is the same thing as having tangent of 25 degrees. And when you have these types of problems that are relating cotangent of an angle to tangent of a known angle, it's a good idea to look at the cofunction formulas, because we do have one that has cotangent of theta, and it's relating it to tangent of some angle, in this case pi over 2 minus theta. Now it's given in radians, but we can always translate that into degrees. Pi is 180, so 180 divided by 2 is 90. Okay, so this formula might as well say tangent of 90 degrees minus theta is the same thing as cotangent of theta. Okay. So because in the problem that we're trying to work with, we have cotangent of theta the same as that formula, and then tangent of some angle, we're going to be using the formula to help us with part A. So let me just write that down. For part A, the formula that we're using is, we'll start with cotangent. Cotangent of theta equals tangent of 90 degrees minus theta. And it's a cofunction formula. Now if we compare it against what we have cotangent of theta is equal to tangent of 25 degrees. So if we were to match up the left-hand side, it's exactly the same. And if we match up the right-hand side, that means that this 25 degrees has to be the same as 90 minus theta, 90 degrees minus theta. Okay, so from the formula, we get that 90 degrees minus theta has to equal to 25 degrees. And if we solve for theta, that means that we're going to get theta is equal to, add the theta to both sides and then subtract the 25 from both sides. So we're going to get 65 degrees. All right. And we can always verify that on the calculator. Okay, so let's see, and I think my calculator finally decided to die, but if we, let me just write that on a separate sticky. You can check by plugging this answer back into the original equation. Is it true that cotangent of 65 degrees is equal to tangent of 25 degrees? Again, you can check this, so I'm just going to right here plug into your calculator and see what you get. Let me see if I can bring up an online calculator here to show you guys. I'm just going to rely on an online calculator called Wolfram Alpha. And I'll split the screen so that you guys can see both sides. Share. Take a look at screen one. All right, so cotangent of 65 degrees is this 0.46630076. Okay, so that's what we have so far. And then for tangent of 25 degrees, if you want to write this down, so cotangent of 65 degrees is the 0.466. I'm gonna say approximately 3.1. If I change this now to tangent of 25 degrees, let's see what we get. Okay, tangent of 25 degrees is again the 0.46631 approximately. So yeah, that means we got the correct answer. Okay, so that checks out. That means that theta equals 65 degrees is correct. Is that okay? Do you guys have questions? Should be in degrees on the calculator because we're using degrees here on paper. We haven't changed it to radians on paper. Okay, so give me a second, guys. I'm actually going to change the batteries on my calculator really quick. That way it's easier for me to share these values with you. Okay. Right, so the calculator is up and running. We should be okay for the rest of the problems. For part B, we have sine of theta is equal to cosine of negative 30 degrees. So again, we want to refer to the formulas and identities to see what formula would we want to apply for this one. So if you again take a look at the cofunction formula, there is on the second column, the first equation has a sine theta just like what we have on the left hand side. And in the formula, that is equal to cosine of pi over 2 minus theta. So meaning it's equal to cosine of 90 degrees minus theta. So that's what we're going to be using here because it's the one that comes the closest to what we currently have. So then I'll write down the formula that we're using. And that is, I'll write sine theta first on the left-hand side because that's what we have. Sine of theta is equal to cosine of the formula has 90 degrees minus theta. And this is again a cofunction formula. Okay. So comparing it against what we're given, we have sine of theta is equal to cosine of negative 30 degrees. And so setting both right-hand sides equal to each other, or in order for this equation to be exactly the same as the formula, that requires that this negative 30 degrees is the same thing as 90 minus theta. So here we're going to get 90 degrees minus theta is equal to negative 30. And again, solving for theta, that means add theta to both sides and then add 30 to both sides. So we're going to get theta is equal to 90 plus 30, which is going to give us 120 degrees. All right, so we check. We want to check if sine of this angle that we got here, so just make sure that you're working in degree mode. I'm going to change mine to degree mode. Is it true that sine of 120 degrees, so here's sine of 120 degrees, is the same thing as cosine of negative 30 degrees? So cosine of negative 30, yes it is. Thanks to our calculator, we can see that they're exactly the same. So theta equals 120 is correct. Any questions there? And we have one more example that uses the cofunction formulas. Let's part C. I'm going to write it on a sticky because I've run out of space already. But we have cosecant of 3 pi over 4 is equal to secant of x. So looking at the cofunction formulas again, the formula that has secant of the angle would be, let's see, it would be this one here in the first column, the second equation. That's the one that has secant of an angle. In the formula, it's given as theta. We have x, but the actual letter that's used doesn't really matter, right? As long as we have secant of some unknown angle. So according to the formula, we have secant of an unknown angle x should be equal to cosecant of pi over 2 minus that same angle x. So notice what I'm doing here. I'm looking at this formula, which best matches what I have here. I'm just simply replacing this theta with x because in the problem that we're dealing with x, not theta. And so doing that on the right-hand side of this formula means that I also do it on the left-hand side. So that's just an x. So that's all that I'm doing here. I'm writing it. And just to, because we do have secant on the right-hand side, let me keep the order that's given in the formula. So meaning, let me leave it as cosecant of pi over 2 minus x is equal to secant of x. Because that already best matches the equation that was given to us. All right, so that's a formula. And now we're going to set it against the given information. So we have cosecant of 3 pi over 4 is equal to secant of x. Okay, this is a given. So comparing the left-hand sides now, in order for these two equations to be the same, it requires that pi over 2 minus x is the same thing as 3 pi over 4, because the right-hand sides are already the same, right? So left-hand sides will be the same only if these two are equal. So we get pi over 2 minus x has to be equal to 3 pi over 4. And so now we solve for x. What we can do to both sides is add the x and subtract the 3 pi over 4. So we're going to have pi over 2 minus 3 pi over 4 is equal to x. I'm going to write this as x is equal to. I'm going to multiply top and bottom of the first fraction by a 2 to get the same denominator. That'll give us a 2 pi over 4 minus 3 pi over 4. And that gives us a negative pi over 4. So the answer that we're looking at is negative pi over 4. Let's go ahead and check it before we box it as our final answer. Is it true? So this is a check. Is it true that cosecant of 3 pi over 4 is equal to secant of negative pi over 4? Because it has to be secant of x. Right, so we're going to check that. So cosecant on my calculator, I have to enter it as a 1 over sine. But before I even do that, now we're working back with radians. So I have to change the mode to radian. Once I've done that, I can go back. 1 over sine of 3 pi over 4 gives us about 1.4142. Now if we check what is secant, remember secant we have to enter it as a 1 over cosine. So 1 over cosine, of negative pi over 4. That is exactly the same thing. So this checks out, and that makes our answer of negative pi over 4 correct. It's a little hard to see with the yellow on the yellow sticky note, so I'll box it a different color. Okay. Any questions with this first example? Example number 1. We're going to move away from example number 1 in the cofunction formulas, and now take a look at sum and difference and fundamental. Okay, so example number 2 is telling us if tan of theta is negative 5 over 3 and theta is in quadrant number 2, find each function value. So for these types of problems, it's always a good idea to first draw what is the given. And so I'm actually going to give that as a guideline for the first step. Draw the given. So we're talking about an angle that is in quadrant number 2. Let's say this is my x-axis and this is my y-axis. The vertex is at the origin. The initial side of the angle is on the positive x-axis. And then we have an angle that terminates in quadrant number 2, which we're calling theta. And we also have information about that angle. They tell us that tangent is negative 5 over 3. Now tangent, if you recall, we use always the reference angle. So we draw a right triangle here. And tangent of the angle is opposite over adjacent, right? SOHCAHTOA. So opposite over adjacent. And this is saying that the opposite side is going to be either 5 or negative 5, and the adjacent side is 3 or negative 3. Now to determine which part is positive or negative, the opposite side is going up in the positive y direction. So this has to be the positive 5. That's in contrast to the adjacent side. The adjacent side goes in the negative x direction, so that one has to be the negative 3. So this 5 and negative 3 we're getting from here. It's the opposite over the adjacent for tangent. The hypotenuse we can find by performing Pythagorean theorem. So we're going to get 5 squared plus negative 3 squared is equal to the hypotenuse squared, which I'll just call a c. And that means that we're going to have c is equal to the square root of 25 plus 9, which is 34. Okay, so it's the square root of 34 that we have there. Now, why am I labeling that? Well, notice now what we have to find. Okay, so this was our step number 1. We're going to draw the given information. For the next step, we look at what is the given. What is the goal? We need to find what is sine of theta. Okay. And we were able to find that thanks to these values that we've drawn on the diagram, because sine is opposite over hypotenuse, right? And the opposite side is 5, and we found the hypotenuse to be square root of 34. And then we want to rationalize the denominator. We don't like to have radicals in the denominator, so multiply top and bottom by square root of 34. And that's going to give us that sine of theta is equal to 5 square root of 34 over 34. Questions there for part K? Okay, for B, they're asking us for what is secant of angle theta. Remember that secant is the reciprocal of cosine. And cosine is usually, is always, I shouldn't say usually, cosine is always adjacent over hypotenuse. So that means that secant has to be hypotenuse over adjacent. And so hypotenuse over adjacent, that is going to be square root of 34 over negative 3. Any questions there? And finally, we have cotangent of negative theta. Now remember, we don't like to have negatives inside of the argument, negative in front of the angle. So we have to remember whether cotangent is an even or odd function. Well, that's what's nice about those formulas and identity sheet is that we have this section called even and odd formulas that tell you precisely that. Okay, so when we were graphing, we learned that sine of negative of an angle, because sine is odd, we can bring the negative in front. But with cosine, since cosine is even, then the negative simply disappears. Okay, so sine was odd, cosine was even. Tangent was also odd. When the negative is inside of the argument, that means we can pull it out. Okay, so tangent was also odd. And here we have a summary of the even odd properties of cosecant, secant, cotangent. In our case, we're interested in cotangent. Right? Cotangent of negative theta is negative cotan theta. So this is going to be negative cotangent theta. And that's by odd formula. Okay, so now that we know that that's what we're interested in finding, I'm going to take negative and then look at the picture. Cotangent, remember, is the reciprocal of tan. So if tangent is opposite over adjacent, then cotangent has to be adjacent over opposite. So the adjacent is negative 3, the opposite is 5, and we get negative 3 over 5. But then negative of a negative becomes positive, so we get 3 over 5. And that's for cotangent of negative theta. Is that okay? Do you guys have questions? So for this one, we didn't use, we didn't really rely on too much new information or new formulas. We just relied on the odd function and on the fact that secant is reciprocal of cosine and cotangent is reciprocal of tan. Here's example number 3. This one is saying, suppose that sine of s is 3 over 5, cosine of t is negative 12 over 13, and both s and t are in quadrant number 2. find cosine of s plus t. So just like what we did in example number 2, I'm going to have the first step be just drawing the given information. Okay, so I'm going to draw the given info. And so we're talking about two different angles, right? There's S and there's T. So let's start with drawing the information that's pertinent to S. Guys, let me just take care of the background noise. Okay, so we'll start with angle S. Here's our x-axis, here's our y-axis, vertex at the origin, initial side on the positive x-axis. And they tell us that S terminates in quadrant number 2. Okay, so I'm actually going to color code these. Color code S in yellow, and then we'll color code T in orange once we draw the picture for it. But this is angle S terminating in quadrant number 2. Now the information regarding S is that sine of the angle is 3/5. So again, remember, sine is opposite over hypotenuse. So we look at the reference angle and draw the right triangle that involves that reference angle. We're going to get that the opposite side is 3 and the hypotenuse is 5, right? Just from this given. Now, using Pythagorean theorem, we can find the missing side of the triangle. That would be a squared plus 3 squared is equal to 5 squared, which means that a squared plus 9 is equal to 25, which means that a squared is equal to 16. And that means that a can be plus or minus square root of 16, right? Because when we take the square root, we have to remember it's plus or minus. So it could be plus or minus 4. Now in this case, because we're going in the negative x direction, we would want to pick a as -4. Okay, so I'll write this on the side. This is because the adjacent side is on the negative x direction. So this side here is -4. All right, and so now we have all the possible information that we could have about angle S. Let's try drawing the diagram for angle T. It's also going to be in quadrant number 2. Right, so vertex at the origin, initial side on the positive x-axis, and the terminal side is somewhere in quadrant number 2. This is for angle T now. Now the information that we have about angle T is that cosine of that angle is -12/13. So if we draw this right triangle, cosine is adjacent over hypotenuse. So the adjacent side is either going to be positive or -12. And the hypotenuse is always positive, so it definitely needs to be +13. That means that the negative is forced on the adjacent side. And that makes sense because we are going in the negative x direction. Okay, so -12 for adjacent side, 13 for hypotenuse. We have one piece of missing information on that triangle that we can find with Pythagorean theorem. So we have negative 12 squared plus this opposite side, which we'll call b. So b squared is equal to the hypotenuse squared. That means that 144 plus b squared is equal to 169. That means that b squared is going to be 169 minus 144, which is going to give us 25. And then that means that b can be plus or minus square root of 25, or in other words, plus or minus 5. Since we're going, well, what do you guys think? Should we pick the negative or the positive 5 for this side here?
Positive.
Yeah, very good, the positive. And why would we want to choose positive over negative?
Because it's in the y direction.
Yeah, good, because it's going up in the positive y direction. And so so b equals 5 because the opposite side is up in the positive y direction. Okay, so now we have diagrams for both angles. We know all of the information regarding the trig functions, or we can figure all that information out from these diagrams that we have drawn. So for the next step, we want to identify what formulas we're going to be needing. Okay, so we're going to identify the needed formula or formulas. So for that, we're going to look back and identify the goal. So this is the given. The goal is to find cosine of angle S plus T. Cosine of S plus T. Do you guys see any formula on this sheet that might have something like cosine of S plus, or cosine of one angle plus cosine of an, plus, let me start over. Cosine of one angle plus another angle, even if it's not the S and T. If it's just other letters, but do you see cosine of two angles anywhere on here? Yeah, thank you, good, Mauricio. Thank you on chat. If we take a look at the sum and difference formulas, there's something that looks kind of like it. The second one, the second formula, has cosine of an angle alpha plus or minus another angle beta. Okay, so this actually has two different formulas compacted into one. And that they do that to save some room so that they're not rewriting the whole thing if the only thing that is changing is a sign. But basically, when you look at the top symbol on the left-hand side, that means that we also look at the top symbol on the right-hand side. And if you look on the bottom symbol on the left-hand side, then we look at the bottom symbol on the right-hand side as well. So there are two formulas that are happening here, and I'll write them on a separate sticky so we can figure out what they are. I'm going to change the alpha and beta to A and B to make it simple for ourselves to see. Cosine of an angle A plus an angle B is equal to cosine of A, cosine of B, and since we use top symbol, then on the right hand side we also use top symbol, which is minus sine A, sine B. So that's one formula. The other formula is cosine of A minus B, which is the bottom symbol. So that means that on the right hand side we also use the symbol. Cosine A, cosine B, plus sine A, sine B. Sorry guys. So these two are packed into this one formula. Now we want cosine of an angle plus another angle. So the one that best fits our needs is this first one. So let's write that down. And the formula that's needed is going to be cosine of, we'll write it in terms of s's and t's. Okay, so cosine of s plus t. That means that we'll have cosine of the first angle, which is in our case s, times cosine of the second angle, which is t. And I'll put parentheses around the angles, that way it's easier for us to identify the what we're working with. And we have minus sine of the first angle, which is s, times sine of the second angle, which is t. All right. Now the next step is to apply the formula. All right. So we apply the formula. We want cosine of s plus t. And that's going to be cosine of s. Cosine of s, we can figure out what it is by looking at the first diagram. Okay, so I'm just going to start color coding things here. Cosine of s from this diagram means adjacent over hypotenuse. So we're going to get negative 4 over 5. And that's from this first diagram. Then cosine of t, to figure out cosine of t, we can either look at the second diagram or we can just look at the given. Cosine of t was given to us as negative 12 over 13. So cosine of t is negative 12 over 13, which I'll color code green, and that becomes 6. Then we have minus sine of angle s. Again, if we go back to this first picture, s, we have sine of, well, okay, we can do it from the picture, which is opposite over hypotenuse, 3 over 5, but we also have it here as a given, 3 over 5. Sorry guys, my doggies are very hyperactive right now. Let me see if I can get them out so that we don't have all this background noise going on. Right, so there's one more, sine of angle t. And I'll color code that in orange. So for sine of angle t, we can go back to the second diagram, and then sine will be opposite over hypotenuse, which is a 5 over 13. So any questions there about how are we using the formula? Why are we using that formula? Where the values are coming from?
Yeah, can you explain why you use that formula?
Yeah, so we chose the cosine of s plus t because that was what we were required to find, cosine of s plus t. And so from the diagrams alone, we are not able to figure out what is cosine of s plus t because these represent individually like angle s and angle t separately. So in order to figure out cosine of the sum of the angles, we're going to have to rely on one of our sum and difference formulas. In particular, this first one that we unpacked from this first one is cosine of a plus b is cosine a, cosine b minus sine a, sine b. So that's what we wrote down here, but with the s's and t's instead of a's and b's.
I see it. Thank you.
Mhm. Any other questions? All right, so we're not completely done because we've just applied the formula, but we still need to kind of simplify our results. So I guess that could be like a step 4, but I won't write it as step 4. I'll just go ahead and simplify. If we multiply negative times negative, we'll get a positive answer. And then 4 times 12 will be a 48. 5 times 13, that's going to be a, what? Let's see, that's a 50 plus a 15, so 65. And then we have minus 3 times a 5, that's a 15. 5 times a 13, that's going to be the same as 5 times 13, so that's 65. Right, and then they have the same denominator, so that means we can subtract across the numerators. We're going to have a 33 over 65. So that's our final answer. Cosine of s plus t is equal to 33 over 65. Okay. Any questions? Let's take a look at example number 4. It's a similar problem. We have, suppose that A and B are angles in standard position, such that sine of angle A is 4 over 5, and let's see, and A is between pi over 2 and pi. Cosine of angle B is negative 5 over 13, and B is between pi and 3 pi over 2. And there's 3 things that we need to find. Sine of A over B, the quadrant of A plus B, and tangent of A plus B. And so we're actually going to do those a little bit out of order. We're going to take care of A and C first, and then take a look at what is the quadrant of A plus B. Because the only way that we'll be able to figure that out is if we already have computed A and C. And so this was just like a typo on my part. It should have been listed sine of A plus B as A, tangent of A plus B as part B, and then the last part should have been the quadrant of A plus B. And so, so we'll do it in that order. Now, let me just try to fix the focus a little. I think it's blurry. There we go. That's a lot better. Okay. So we're going to go through the same steps as the previous problem. First, we're going to draw what is the given information. So that's our step 1. We have 2 angles. I'll start with angle A. And angle A terminates between pi over 2 and pi. Which quadrant is that going to be? If something is between pi over 2 and pi, what quadrant is that?
Is that quadrant 2?
Yeah, quadrant 2, very good. Because remember, this is 0, this is pi over 2, and this is pi. So between pi over 2 and pi, that's quadrant number 2. So we have an angle here, and it's called A. Here's A. Now, what information do we know about A? Well, we know that sine of angle A is 4 over 5. So that means that we have opposite is going to be 4 over hypotenuse. That is going to be 5, because that's sine. The adjacent side we're able to find using the Pythagorean theorem. So let's give that a try. We're going to have a squared plus 4 squared is equal to 5 squared. That means that a squared plus 16 is equal to 25. That means that a squared is equal to 9. And that means that a can be plus or minus square root of 9, which is plus or minus 3. Now in our case, since we're going in the negative x direction, that means that we want this to be negative 3. All right, so that's one angle. The next angle, angle B, let's see, for B we have it's between pi and 3 pi over 2. So which quadrant will that be in?
Quadrant 3.
Quadrant 3, yep, good, because this is 0, pi over 2, pi, 3 pi over 2. So if it's between pi and 3 pi over 2, we're down here in this area in quadrant number 3. Right, so it's going to be vertex at the origin, initial side on the positive x-axis, and then terminal side will be somewhere down here. And so this is now okay. And what information do we have about B? Well, we have the cosine. Now remember, for an angle that's in quadrant number 3, we draw the right triangle between the terminal side and the negative x-axis, so that we're considering this reference angle. And then cosine is going to be adjacent over hypotenuse. So the adjacent side has to be negative because we're in the negative x direction. The hypotenuse is always positive. So that one is going to be positive 13. And now we'd like to find the missing side of that triangle. So we're going to apply Pythagorean theorem. We're going to have negative 5 squared plus b squared is equal to 13 squared. That's going to be a 25 plus b squared is equal to 169. That means that b squared will be equal to 144 because we subtract the 25 from both sides. And that means that b could be plus or minus square root of 40 of 144, which is plus or minus 12. Now, because we have b as the opposite side, what should be the sign? Should it be positive or negative? What do you guys think? Does this have a
Should be negative.
negative? Very good, because we're going down in the negative y direction. Good, thank you. This is negative 12. Okay, so now we have all the information that we need. Now for the next step, we're going to identify which formulas are necessary. Now part A has sine of a plus b. Okay, so for part A, we're going to be taking a look at a sum and difference formula as well. but it's going to be for sine. Okay, so let's go back to the sum and difference formulas. In this case, what this is saying is that if you have sine of A plus B, that it's going to be sine of A cosine of B. Take the top symbol again, because we took the top symbol on the left-hand side, so that'll be plus cosine of A sine of B. So the formula that we're using, again, I'm just going to write it over here in terms of the angles that we have, is sine of A plus B, sine of A plus B equals sine of A cosine B. And then top symbol is plus cosine A cosine B. Cosine A sine B. That's the formula we're going to use. And we're going to apply it. So this is our step 3. I'm going to separate this. I'm going to call this part A, step 2, because we do have a tangent that we need to find. Okay, so this is the step 2 for part A. Now the step 3 is to apply the formula. And that means that we're going to have sine of A plus B is equal to sine of A. Now, sine of A was given to us. If you take a look here at the top, it's a 4/5. You could also just look at this first diagram, because that's the one that involves angle A, and see that sine will be opposite over hypotenuse, 4/5. Okay, so this first one, the sine of A, is going to be 4/5. Then cosine of B, which I'll color code blue, we were also given cosine B, right? It was -5/13. We could also read it from the second diagram, adjacent over hypotenuse, -5/13. Then we have plus cosine of A. So we'll go back to the first diagram. Cosine of A is going to be adjacent over hypotenuse. So that'll be a -3/5. And then finally we have sine of B. So sine of angle B, we can look at the second diagram. That's going to be opposite over hypotenuse. So -12/13. So questions up to that point? All right, so let's simplify. Positive and negative becomes negative. 4 times 5 is 20. 5 times 13 is going to give us a 65. Then negative times negative is positive. 3 times 12 is 36. 5 times 13 is 65. And so -20 plus 36 is going to be a +16/65. And so we have sine of A plus B is going to be 16/65. Is that okay? Any questions there? Right. The next part, as I mentioned earlier, we're going to compute tangent of A plus B first. So now we want a formula that involves tangent of A plus B. So we can go back to the sum and difference formula, and there is one that reads precisely that. It says tangent of A plus B, so we're taking the top symbol. Tangent of A plus B is equal to tangent of A, top symbol is plus tangent of B, over 1, and then top symbol in this case is minus. So 1 minus tangent of A times tangent of B. Okay, so we're going to write that formula down. The formula is tangent of A plus B is equal to, again, tangent of A plus tangent of B. And then the whole thing is divided by 1 minus tangent of A times tangent of B. That's the formula. Is this okay? Do you guys have questions? Okay, so we picked out what formula we need. Now we're going to apply it. Okay, this is step 3 for part C. Applying it, we get tangent of A plus B will be equal to tangent of A. So that means we have to go to the first diagram. That's the one that involves angle A. And look at what is tangent. Tangent will be opposite over adjacent. So 4 over negative 3. And we get 4 over negative 3. That's this first part. Then we have plus tangent of B. Okay, so tangent of B, we're going to figure out from the second diagram. It'll be opposite over adjacent. So that's a negative 12 over negative 5. But negative over negative becomes positive. So we're going to have just 12 over 5. So plus 12 over 5. That's the tangent B part. And then we have divided by, this is divided by 1 minus tangent of A again. And remember, we already know what tangent of A because we used it in the numerator. It was this 4 over negative 3, which I'll just write as negative 4 over 3, times tangent of B. And tangent of B we also used in the numerator. We found it to be 12 over 5. All right, so questions here? Okay, let's simplify as much as we can. I'm going to start by multiplying in the denominator these two fractions together. We're going to get a negative 4 over 3 plus 12 over 5, which is the same. That I'm going to keep the same for now. I'm not going to simplify anything there. In the denominator, we're going to have a 1. Negative and negative will become positive. Then 4 times 12 gives us 48. And then 3 times 5 gives us 15. Okay, so we end up with that. Now there are multiple ways that you can simplify this complex fraction. So anytime that you have fractions within a larger fraction, they call that a complex fraction. So there are multiple ways that you can simplify that. My favorite one is to multiply top and bottom by the least common denominator of all of the fractions. So if I look at the negative 4 over 3, the 12 over 15, and the 48 over 15, what is the least common denominator between these three? 3, 5, and 15. What's the LCD there?
$15.
15, good, yeah. So then we take the LCD and we multiply it to both numerator and denominator, making sure to distribute to all of the terms. And so when we do that, we're going to get 15 distributed to the negative 4 over 3. That's like a 15 divided by 3 is 5. And then 5 times the negative 4 is negative 20. We'll get negative 20 by distributing here. Then 15 divided by 5 is 3. And 3 times a 12, that's a 36. So plus 36. Over, distribute now in the denominator. 1 times 15 is 15. And then 15 times 48 over 15, so that's 15 divided by 15 is 1. 1 times 48 is just 48. And so we get that. Now there are no more fractions. We can just add numerator and denominator. The negative 20 plus 36 will give us a positive 16. And then 15 plus 48, that's going to give us a 65. So we get a final answer that says tangent of a plus b is equal to 16 over 65. Actually, hold on. That seems a little suspicious to me. Did I make a mistake? Did you guys catch a mistake anywhere?
48 plus 15 is 63.
It is 63. Thank you. Yes. This should be 60. That should be 63. The reason why it seemed a little suspicious to me is because we were getting the same thing as for sine, right? Tangent and sine can't be the same thing. Good. Thank you. All right. Any questions there? Right, now we have one last step, the quadrant of a plus b. What is the quadrant of a plus b? Well, the key here is to notice that the angle a plus b has a sine function that is positive and a tangent function that is also positive. Okay, so I'll write notice a plus b has sine of a plus b positive and tangent of a plus b positive. Okay. So now we can think about, if we consider the 4 quadrants, right? In quadrant number 1, sine is what? Sine of any angle in this quadrant is what? Positive or negative?
Positive.
Positive, very good. Yep, it's positive. What about tangent? Remember, it's going to be opposite over adjacent. The opposite side, which is somewhere up here in the positive y, will be positive, and the adjacent side will be in the positive x direction. So that one will also be positive. Okay, so if you want, if you ever forget, you can always draw this right triangle and say, okay, this is positive, hypotenuse is always positive. So sine is going to be positive, and tangent is going to be positive. So it seems like quadrant number 1 is going to be our answer. The only thing that we need to do is verify that this doesn't also happen in a different quadrant, because then we'll have more than one possibility. In quadrant number 2, if we draw our triangle, we have the opposite side positive, but the adjacent side negative, and hypotenuse is always positive. So the sine will still be positive because we'll have opposite over hypotenuse, but then the tangent will be opposite over adjacent, which will be negative, right? So that one would not be a possibility. Quadrant number 2 would not be a possibility. Then if we check quadrant 3, okay, the adjacent side is still negative. The opposite side is negative. Hypotenuse is always positive. So down here, the sine is opposite over hypotenuse. So that's going to be negative over positive, which means it's negative. And already I can see then that this won't qualify because we need sine of a plus b to be positive, right? And this is already negative. So that is disqualified. We have one more quadrant to check. In the 4th quadrant, we have adjacent side positive, but then opposite side goes in the negative direction. And so here, again, we're going to get sine is opposite, which is negative, over hypotenuse, which is positive. So we'll get a sine which is negative. So quadrant number 4 is also disqualified. So that means that the only place where both the sine and the tangent are positive is in quadrant number 1. Yes, very good. Thank you, Lee. If you notice on the chat, we have ASCC. That means all are positive in the first. Sine is positive in the second. Tangent is positive in the third. And cosine is positive in the fourth. But if you ever forget, remember you can just draw these triangles and label according to the x's and y's. Okay. Any questions? This one, similar type of problem, we're just going to be using a different type of formula because we have given that cosine of theta is 3 over 5 and sine of theta is negative. Find sine of 2 theta, cosine 2 theta, and tangent 2 theta. Okay, so we're going to start with the usual first step, which is to draw the given. And here's x, here's y. Now, they don't tell us explicitly what quadrant the angle theta is found in. But notice what they did say. They said cosine theta is 3 over 5. So that means cosine theta is positive and sine of theta is negative. So in which quadrant do we have a positive cosine but a negative sine? Meaning, if we look at the cosine, remember cosine is adjacent over hypotenuse, and the hypotenuse is always positive, right? So that means that adjacent has to be the one that's positive. So adjacent over hypotenuse has to be positive, and this guy's always positive, so adjacent has to be positive. So where is cosine? Let's start with just that. Where is cosine positive?
One and four.
1 and 4, very good. So we have as candidates quadrant 1 and quadrant 4, okay, because that has an adjacent side that is on the positive x-axis. Now for sine of theta, we have a negative, and remember sine is opposite over hypotenuse. Sorry, and that's negative. So if hypotenuse is always positive, that means that the opposite side is forced to be negative, right? So which of these two quadrants satisfies that the opposite side is negative? Let's draw it. We look at quadrant 1. This is positive, and this is positive. And this is always positive. Hypotenuse is always positive. So here, sine of theta being negative is not satisfied because the opposite side would be positive. Okay, so this one can't be it. If we take a look at quadrant number 4, we have adjacent side is positive, opposite side is negative, and hypotenuse is always positive. So here we do satisfy opposite over hypotenuse is negative because the opposite side is negative over hypotenuse is positive, so we satisfy this. Is that okay? Does that make sense? right, so I'm going to erase this part because we know it's not in quadrant number 1. It's going to be in quadrant number 4. I have vertex at the origin, initial side on the positive x-axis, and we have the angle terminating in quadrant number 4. And then for this reference angle, we have that cosine will be 3/5. So that means the adjacent side will be 3. The hypotenuse will be 5. And the opposite side we can figure out by, I'll leave the negative there because we know it for sure needs to be negative. We can find out by using Pythagorean theorem. We'll have 3 squared plus b squared is equal to 5 squared. 9 plus b squared is equal to 25. B squared is equal to 16. And that means that b has to be -4. So this here is -4. Questions there with the diagram? For the next step, we need to identify which formula or formulas are necessary to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. If you look at the double angle formulas, we have some that have the sine 2 theta, cosine 2 theta, tangent 2 theta on the left-hand side precisely, right? So we're going to be focusing on double angle formulas. And I'll start with the sine of 2 theta. Yeah, so the formula sine of 2 theta, just by transferring over, that's equal to 2 sine theta cosine theta. So this is 2 sine theta cosine theta. And we can figure out what the sine theta and cosine theta will be from the diagram. So sine of angle theta, that would mean opposite over hypotenuse. That's a -4/5. And so this is the same as this. And then cosine of angle theta, you can also read it from the diagram, or you can write it down from the given. It's given to us as a 3/5. Okay, so now let's simplify. We have a 2 times negative times positive will give us negative. So that'll be -12 over 5 times 5 is 25. And then finally, this you can treat as a 2/1. So we have 2 times -12, that'll be a -24 over 1 times 25, that's a 25. So one of our answers, or one part, is that sine of 2 theta is equal to a -24 over 25. All right, so that's for sine 2 theta. We need to find cosine 2 theta. And cosine 2 theta gets a little bit interesting because there's actually 3 different versions that we can use to find cosine of 2 theta. So this is version 1, this is version 2, this is version 3. My suggestion is to use the version that agrees with the information that was given to you. So if we look here, they gave us cosine theta only. All the other ones we are able to find from the diagram, but if we're just using the given that was explicitly given, we can go back and say, well, version 2 uses only cosine, and that was explicitly given. Okay, so we're gonna go for version number 2. And that is cosine of 2 theta is equal to 2 times cosine squared theta minus 1. Okay, so let me write this is double angle formula for cosine. And this is version 2. So if you want to go back and refer to the formulas, that's where it's coming from. Okay, so now applying it, remember that when we have this notation, cosine squared, it actually means take cosine of the angle theta and then square the result and then have minus 1. Okay, so this is going to be a 2 times cosine theta was given to us as a 3/5. So we're going to write 3/5 squared minus 1. So let's see, this part, same as this part. Right, then 3 squared is a 9, 5 squared is a 25. And this is the same thing as a 2/1. So 2 times 9 is 18. Over 1 times 25, that's 25. And then we have minus 1. The 1 we can write as a 25/25. So doing that, we get 18 minus 25, that's 17. Or I should say negative 17 over 25. Sorry, not negative 17, negative 7. Right, negative 7 over 25. So that's our final answer for that part. Cosine of 2 theta is negative 7/25. Questions there? Okay. Now for this third part, we still need to find tangent of 2 theta. There's a couple ways that you can approach it. One of them is to use the double angle formula for tan, but there's an even shorter way using a different formula. Can you guys see which formula would make our work a lot easier to find tangent of 2 theta? I'll give you a hint. It's one of the fundamental equations, one of the fundamental identities.
Sine over cosine.
Yeah, very good. Remember that tangent of any angle is the same as sine of the same angle divided by divided by cosine of that same angle. So even though we have theta here, technically if we were to have 2 theta, then we would just replace everywhere there's a theta with 2 theta. Okay, so in other words, we could use a formula that says tangent of 2 theta is the same as sine of 2 theta divided by cosine of 2 theta. And this is a fundamental identity. Now this is a lot shorter, a lot less work because we have already computed sine of 2 theta and cosine of 2 theta. So we can just take their values and plug them into the appropriate spot. Okay, so we're going to get tangent of 2 theta is equal to sine of 2 theta in the numerator, so that would be negative 24/25, divided by cosine of 2 theta in the denominator, so that's negative 7/25, And then remember that when you divide by a fraction, that's the same thing as multiplying by reciprocal. We get negative 24 over 25 times a negative 25 over 7. Okay, I'm just taking the reciprocal of the denominator. Negative times negative becomes positive. The 25 in the numerator cancels out the 25 in the denominator, leaving us with just a positive 24 over 7. So as our final answer for this, we get tan of 2 theta is 24 over 7. Any questions there? Right, we're going to consider one last example. If you go to page number 6, it'll be example number 8. Examples 6 and 7 we'll consider next time that we meet live. The part 2 of today's lecture picks up on page 7. Okay, so technically we're going to have examples 6 and 7 that are going to get skipped over, but then we'll come back to them next Monday. Okay. But for example number 8, it reads, given that cosine theta is 2 over 3, with theta being between 3 pi over 2 and 2 pi, find sine of theta over 2, cosine of theta over 2, and tangent of theta over 2. All right. So again, we're gonna draw the given. That'll be our first step. The angle is between 3 pi over 2 and 2 pi. So which quadrant is that going to be?
Quadrant 4.
Very good. Yeah, quadrant 4. Quadrant 4. This is 0. This is pi over 2. This is pi. This is 3 pi over 2. I drew that too long, so let me just do it up here. And then this is 2 pi once we make it all the way back. So if it's between 3 pi over 2 and 2 pi, that means quadrant number 4. So we have initial side on the positive x-axis. This is our x-axis. I'll erase this so that there's not too much going on. And then we have the angle terminating in quadrant number 4, somewhere there. And that is called theta. That means that when we're considering the opposite, adjacent, and hypotenuse, we're considering this right triangle here. Now the cosine is given to us as a 2 over 3. So that means the adjacent side is 2 and the hypotenuse is 3. The opposite side we can find by applying our Pythagorean theorem. So that'll be a 2 squared plus b squared is equal to 3 squared. That's a 4 plus b squared is equal to 9. That means that b squared is equal to 5. And that means that b can be plus or minus square root of 5. But because we're going down in the negative y direction, this is going to be negative radical 5. Negative square root of 5. Okay, so that's all the information that we know. Let's take a look at what formula should we apply. And we need to find sine of theta over 2. Here's our formula sheet. I want you guys to look at the top left, right-hand corner. There is a formula that that sine of theta over 2 is equal to plus or minus square root of 1 minus cosine theta over 2. And so that's what we're going to use here. Formula. Is sine of theta over 2 is equal to plus or minus square root of 1 minus cosine theta over 2. And I'll write it, this is a half angle formula. Now, in order to apply it, we're going to write sine of theta over 2 is equal to, we have to pick only one symbol. We can't keep both. And whether we pick plus or minus is going to depend on where does the angle theta over 2 terminate. Okay. So on this side, I'm going to write some important work. It'll be in a different color. This is our side work. And the question is, where is theta over 2? In which quadrant? Well, theta is given to us as it's between 3 pi over 2 and 2 pi, right? So if I divide theta over 2, if I divide theta by 2, that means I can divide all 3 parts of the inequality by 2. And that means that we would have 3 pi over 4 is less than theta over 2, which is less than pi. So if it's between 3 pi over 4 and pi, we can draw that on the plane. This is 0. Let's say this is pi over 2. Halfway would be pi over 4. And then this is pi. Halfway would be 3 pi over 4. So we're saying the angle theta over 2 is found somewhere between the 3 pi over 4 and the pi, somewhere in this region. Which quadrant is that region in? Well, that would be quadrant number 2, right? Because this is quadrant 1, this is quadrant 2. This whole thing is quadrant 2. So even though technically the angle is between 3 pi over 4 and pi, it's still just quadrant 2. In quadrant 2. So then that helps us, because if we're taking sine of an angle that is in quadrant 2, what is that going to be? Is that going to be positive or negative?
Negative.
Well, let's be careful, because then sine is the opposite side, right? And the opposite side is here. So it'll be opposite, which is in the positive y direction, over hypotenuse, which is also positive. So this is going to be positive square root of 1 minus cosine theta all over 2. And then I'll write here, because theta over 2 is in quadrant 2. And sine is positive in quadrants 2. Okay. So now that we've figured that out, we can plug in the value of cosine theta by going back to our original diagram. Okay, so for the angle theta, cosine is adjacent, which is the 2, over hypotenuse, which is 3. So this is minus 2 over 3, and then divided by 2. So this becomes the square root of 1 minus 2/3, that's just 1/3 divided by 2. Then 1/3 divided by 2, that's the same thing as taking 1/3 times 1/2. So we get the square root of 1/6. And then from there, we just write sine of theta over 2 is square root, we can simplify this into square root of 1 over square root of 6. So this is 1 over square root of 6. And when we rationalize, we're going to get square root of 6 over 6. So sine of theta over 2 is going to be the square root of 6 over 6. All right.